Next thing we're going to talk about is molecular orbital theory again, but now just looking at diatomic molecules that are made up of different atoms, so heteronuclear diatomics. So the concept will be the same. But the math will just end up a little bit different. So heteronuclear diatomics, you're going to do everything exactly the same, except that when you do this linear combination of atomic orbitals, when they were the same atoms, homonuclear, Ca would equal Cb, because you'd have an equal contribution from those two wave functions, because your orbital would end up symmetric. But now Ca isn't going to equal Cb. You're going to have a greater probability of finding the electrons closer to one atom or the other, and it's always going to be based on the electronegativity. So for bonding orbitals, if the electronegativity of A is greater than B, then Ca squared will be greater than Cb squared, which is the same thing as saying you're going to have a greater probability of finding the electrons on the atom labeled A rather than B. And it'll just be the opposite for the anti-bonding. If the electronegativity of A is greater than B, then you're going to have less probability of finding the electrons on A than on B in the anti-bonding orbitals. So electronegativity is a concept that is not a physical observable, which is just the same thing as saying it's not something that has a defined value. So there are different ways of approaching what electronegativity is. It creates this situation. So in our last diagrams, the atomic orbitals always started at the same place and you went up and down, so this diagram was symmetric. But now if you have different electronegativity, you're going to start at a lower energy depending on the electronegativity with the atomic orbitals that you're adding, and so you get a kind of skewed looking molecular orbital diagram. There are many ways to define electronegativity. This is the Pauli way, and this is the Mulliken, most of which will be calculated whenever you do a molecular orbital calculation. When we look at this to really think about what it's a measure of, this equation says that the difference in electronegativity of atom A and B, the absolute value, is related to how much energy it takes to break an AB bond versus an AA or a BB bond. So when we look over here at this self-test, wants us to do an analysis and figure out the difference in electronegativity between hydrogen and bromine. We know from this diagram right here that should be about 0.7 because hydrogen is 2.2 and bromine is 2.96. So when we do that calculation, they give us the dissociation energy for the hydrogen diatomic in electron volts. They give it to us for bromine and HBr in kilojoules per mole. But this equation and the units of electronegativity are given in electron volts. So we'll convert each of these to electron volts. We'll put in, this is the bond dissociation energy in electron volts of HBr. This is H2, which just came from the brief illustration right before this. And then this is for Br2. When you plug those in, I got 0.70. So that matches what that diagram would show us. So that difference in electronegativity is going to essentially show you how distorted the molecular orbital is going to be. So let's just go ahead and there will be nothing different. So these molecular orbitals will be just like the molecular orbitals if it's a homonuclear diatomic, in that you'll fill them with Hans rule and Pauli's exclusion principle. Let's just quickly calculate some. So let me see if I can share my screen first. I don't know if I can. No, I can't, sorry. Let me first get WebMo up and then I'll share the screen. Okay. So if I share that screen, let's just do a calculation for carbon monoxide because we know that's a heteronuclear diatomic, so it should be not symmetric. So if we create a job with a carbon atom and an oxygen atom, we'll do everything the same as what we did last time. We'll get the geometry closer to where it should be for its calculation. We'll figure out the best geometry. And then we'll, oops, not done yet. Now we're going to do the molecular orbital calculation. So we'll start with that geometry. Run a new job. The job will be to calculate the molecular orbitals. And now we'll look at them. I won't draw the same diagram, but it'd be the same process. You would take these orbitals, you would take the first one as the lowest energy, and you'd fill them according to energy. This shows us, when we look at the first one, let's look at it. It's a sigma bond, it's symmetric, and there's no node between the nuclei. The next one is, does have a node, so a red and a blue that changes color in between the nuclei, so that's a anti-bonding sigma. Here's a pi bond, another pi bond of the same energy, which would be perpendicular, and then another sigma. This one, it's the easiest to see. This is a sigma bonding, but what you notice is that there's a much greater electron density on atom number 1. We can go back up to our job. Well, I'll just go back to it this way, sorry. We can go back up to that job to realize that atom number 1 is here. And when you go down to the data, it shows you that, I guess we have to do it for the job before this, the one where we did the geometry, just to confirm which atom is 1 and which is 2. You must have to do a frequency analysis. Well, based on our understanding of electronegativity, 1 would be the oxygen and 2 would be carbon. And so when we looked at those MOs, you see you create the diagram the same, everything's the same, you fill it the same. The difference is the orbitals aren't going to be symmetric. So there's nothing different about heteronuclear diatomics in what the definition of an MO is, just that they're going to be asymmetric.